Here we're using a double integral to figure out the area of a region. The region is going to be capital D. The description of D is here. It's the set of points of the form xy such that x is greater than or equal to 0, y is greater than or equal to minus x, and x is less than or equal to 2 minus y squared. I'm going to do this with respect to A. Now, dA sometimes is going to turn into dy dx. Sometimes it's going to turn into dx dy, but there are other choices. With polar coordinates, we'll get r dr d theta. Dy dx, dx dy, r dr d theta are all different ways of writing dA. If you're just given a description like this, you're best off drawing a picture. Let's see, x greater than or equal to 0, so I think I'm going to emphasize quadrants 1 and 4. And let's mark x equals 0. Y equals negative x would be a diagonal line like this. X equals 2 minus y squared should be a parabola cupped this way. If I go over 1, 2 units, I should have the vertex. So if y is 0, x is 2. If x is 0, y would be plus or minus root 2. So let's try to mark in a root 2 there and there. So it should look something like this. Now, x is greater than or equal to 0, so I'm only interested in things occurring to the right. Y is greater than or equal to minus x, so I'm only interested in things in that wedge. X is less than or equal to 2 minus y squared, so I'm only interested in things inside the parabola. I believe that this shape gives us these three conditions. It's the shape which matches each of these three conditions. I know that I could do this with Cal 1 techniques, but there are times when Cal 2 techniques work better, especially when we move to polar, so it's nice to make the transition to Cal 2 techniques already with area. I think I'm going to have to make a decision. Do I want to slice it up dy, or do I want to slice it up dx? Since I have x in terms of y, I think the decision is going to be to slice it up dy. I also think I'm going to have to do two different areas. Let's call them 1 and 2. Because the right-hand side, the right-hand value of x, remains 2 minus y squared, but the left hand changes character. For a while it's 0, for a while it's minus y. The area should be the sum of area 1 plus the sum of area 2. I'll write area 1 as a double integral. I'm slicing it this way, so that's going to be dx dy. This is the point 0, root 2, so y is going from 0 up to the square root of 2. X is going from 0 on this side to 2 minus y squared. And that will be area 1. Let's just follow through with area 1 by itself. We'll worry about area 2 later. This will be the integral from 0 to 2 of 2 minus y squared dy. As a matter of fact, this is the integral that you would have written in Cal 1. Now, that should be 2y minus y cubed over 3 evaluated from 0 to the square root of 2. So that's 2 root 2 minus root 2 cubed is also 2 root 2, but remember over 3. If I get a common denominator, I'd have 6 root 2 minus 2 root 2, so that would be 4 root 2 over 3. Now I've done half of the problem. I've figured out what area 1 is. Let's move on and find area 2. Again, it's going to be a double integral. This time y is going from, well, whatever the y value is here, up to its highest point, which is actually y equal 0. Let's figure out what this point is. You may have guessed it. It is one of those points that people will sometimes guess, but let's actually solve for it. Here we have x equals a minus y. Here we have the same value of x, should be 2 minus y squared. So they should meet when minus y is equal to 2 minus y squared. That happens when y squared minus y minus 2 is 0. This factors as y minus 2 times y plus 1. Now, in this case, y minus 2 is 0 and y is 2. Presumably, that would be this intersection. That's not the one we're interested in. The other intersection would be when y plus 1 is 0. That happens when y is a negative 1. If y is a negative 1, x is the opposite, so it looks like x is 1, and this is going to be the point 1 comma negative 1. So y is going from negative 1 up to 0. The 2 minus y squared is still going to be the point on the right-hand side, but the point on the left-hand side, the x value, is going to be a minus y. And remember that we're doing this dx dy because we're stacking our slices horizontally. So this will be integral from negative 1 to 0 of 2 minus y squared minus a negative y. Now, when we integrate this, we're going to get 2y minus y cubed over 3 plus y squared over 2, and we're evaluating from negative 1 to 0. If I plug in 0, all of the terms will be 0. If I plug in negative 1, 2 times negative 1 is negative 2. Negative 1 cubed is going to be a negative 1, but I have this other negative, so that would be plus 1/3. Negative 1 squared is positive 1, so this would be plus 1/2. Now, on the inside, I think I'm going to have to go with 6 as my denominator. For my numerator, I'd have minus 12 plus 2 plus 3. Minus 12 plus 2 plus 3 should be a minus 7 on the top. But remember that you're subtracting that, so this is actually going to be plus 7/6. Might as well get a common denominator between these two of 6. I'll put the 7 in front. I think it looks nicer that way. This, to get over 6, I would have to turn into 8 root 2. So that would be the area of this particular shape. So double integrals in order to find area.